Yes, mister.
Yes. Go ahead.
I'm just answering you. Yeah, I'm ready.
That's good. That's good. So the lecture for today is resistors in series and parallel. Let's take a quick look at the objective list here. This is objective C.2.A, 1 through 5. So if we can take a quick look over there. That's basically all of this stuff here. And mostly the first three is what we'll be looking at today. And once we do these first three, kind of the 4 and 5 will kind of follow naturally after that. But the idea is we want to understand the behavior of series and parallel combinations of resistors. I'm just gonna hold on. So we're looking to understand series and parallel combinations of resistors. So we've got to understand what we mean by series and parallel. And then we want to be able to tell by looking at a circuit diagram if the resistors are in series or parallel, or in a more complicated diagram, both. We want to figure out what the voltage drops across separate resistors in our circuit are. We want to be able to, and importantly, where we focus mostly on number 3 here, is figuring out the equivalent resistance of a network of resistors. So if we replace 2 resistors in series with one equivalent resistor, what would the resistance of that resistor be? And same thing with parallel. All right, and then once you can do that, then you can use what we already know to calculate voltage, current, and power for any resistor there. And you'll be able to make a simple circuit that produces a current through a certain current through a specified component. And that kind of goes along with the circuit construction worksheet that we've worked on a little bit already. And we're going to revisit that as well at some point soon. Okay, so here we go. Let me put my paper back. Okay, so this first circuit diagram here has 2 resistors. Now, are these resistors in series or in parallel the way they're drawn here?
In series.
Series.
Yeah, these are in series. Right, and a series just means one thing after another, right? So, and that's because the current in this circuit hits one resistor after another, right? So series is just one after another. All right, we've got them. They don't have to be the same, right? They're, in general, they're not going to be the same resistance. This one has a resistance R1. This one has a resistance R2. So the question then we want to know is, if we replace these 2 resistors with just one resistor, but we want the circuit to have the same amount of current flowing through it, what would that resistor's value be? And we call that the equivalent resistance, or REQ for equivalent. So what's the equivalent resistance of these 2 resistors together in series? That's what we're going to look for. So basically, and when we do, later on, when we'll get to more complicated circuits with a bunch of different resistors and a bunch of different configurations, the idea is we can kind of simplify it by converting multiple resistors in series into an equivalent resistor to it, so that we can analyze it. So basically, we would be replacing this circuit with this circuit, right? We're replacing these 2 resistors with one equivalent resistor. So let's see how we can do that. Let's see what we can say about, first of all, there's going to be current flowing through this circuit, right? There's going to be current flowing through resistor 1. There's going to be current flowing through resistor 2. Is there anything we can say about how current 1 and current 2 are related to each other?
Well, current 2 is smaller than current 1.
Is it? Okay. How do we know that, or why do we think that?
Well, isn't that because the voltage drops?
Well, the voltage drops, right? So there's going to be, if we look at the potential here, at the end of resistor 2, it's going to be different than the potential here after resistor 1. But I'm not sure that it follows that the current's going to be smaller here, right? Remember, the current is the amount of charge you know, passing through the resistor or passing through any point in the circuit at a given time?
They both equal the total current. Oh, well, added together, they equal the total current.
Added together, they equal the total current. So what do we know about, one thing we do know about charge is that it's going to be conserved, right? We're not going to have any charge kind of building up anywhere in the circuit. And we're definitely not going to have any charge disappearing. So however much current is passing through this point here in a given time, since there's nowhere else for the current, for the charge to go other than, you know, along this path and also through the second resistor, it's actually got to be the same current, right? When we have a circuit that's a loop, just a simple loop like this, the current has to be the same everywhere in the circuit, right? Otherwise, we'd have charge being created or destroyed at some point, right? The analogy that we have talked about is, you know, like a pipe with water flowing through it, right? And if you have just one loop, right, the amount of water flowing through past one point in the circuit has to be the same as the amount of water flowing past another point. Otherwise, you're going to have water disappearing somewhere, right? And it's the same with charge. In any given loop of a circuit, the charge has to be in a single simple loop like this. The charge has to be the same all the way through. Does that make sense? I thought we had we maybe only briefly discussed that when we were first talking about current.
That makes sense now.
So we do know that the current, we'll call it I, is the current in the circuit, and you know, and that's got to just be the same through resistor 1 and the same through resistor 2. All right, and this is because charge is conserved. It can't build up anywhere or disappear. So we know that the current through each of these has to be the same. Let's look at the potential. We have delta V. Oops. Yeah, delta V is the potential across the battery, going from the negative terminal to the positive terminal. And we also know that, well, what can we say about the potential difference here? There's going to be a potential difference across the first resistor, and there's going to be a potential difference across the second resistor. We remember how we can kind of relate those two to the total potential difference. We said the currents have to be the same. Is the same true about potential drops? And remember, think about the analogy of, you know, a potential drop is kind of like the waterfall in the analogy, right? The water goes from a higher place to a lower place, right? A high potential to a low potential. And when it gets to the end of the circuit, to the negative terminal of the battery, it gets pumped back up to the top. So how can we accurately relate delta V1 and delta V2 to delta V?
Delta V2 is smaller than delta V1.
Well, it might be. We don't know, right? That's actually going to depend on the value of these resistors, right? We know that for any, you know, the definition of resistance, right? Let me put it over here. R equals the potential over the current, right? That's just the definition of resistance. So if the current is the same in both of these, and R2 is bigger than R1, then delta V2 is going to be bigger than delta V1. But what we do know is that the potential drop across 1 plus the potential drop across 2 has to be equal to the potential difference across the battery.
Oh, okay. That's where I went. Okay.
Right? If you think about the analogy, the water and the pipe analogy, right? We start up at the top, right? Potential is like height, So the water starts flowing at the top. It drops down here, right? From some V to some smaller V. And then it drops down here again from that smaller V all the way down to 0, right? Because that's now at the same potential as the negative terminal of the battery. Then it gets pumped back up to the top again by the battery, right? So however much it drops for both of these together has to be the same as the amount that gets pumped back up by the battery. Is one way to think about it. So we know that these two potentials have to add up to be the total potential. So, and I'm going to continue on with this using the definition of resistance, right? If I rearrange this, I know that delta V is just the current times the resistance. So that means the delta V1, well, that's going to be the current 1 times resistor 1. And delta V2 is current 2 times resistor 2, right? So let me rewrite that a little bit. I've got my delta V, that's the potential just from the battery. I1 and I2 are the same, right? We said these two are the same. We can just call it I because they're the same. So I can kind of factor that out. R1 and R2 aren't necessarily the same. Right, so I can say that my potential difference is the current times R1 plus R2. Are we okay with that?
Yes, actually. Makes a lot more sense.
So now let me look over here at my equivalent resistor circuit. Right, I know, well, it's the same battery, right? So I know just from here that delta V equals, just from the definition of resistance, I times R, right? The current through the circuit. And right, we're picking our equivalent resistor so that the current in this circuit is the same as the current in this circuit. So it's the same I times this equivalent resistor.
I saw in the textbook, so sorry. At least. Okay. Oh, okay. Never mind. For equivalent resistors equal every resistor, right? Or at least REQ equals R1 plus R2, and then so on, right?
Yeah. So hold on. Yeah, we'll get to that, right? If we have more than two resistors in series, then you can kind of repeat the process, right? You can change two of them into one equivalent resistor and then make that an equivalent resistor out of the next one. But yeah, you're right. We're getting to that. We're going to generalize it without kind of going into that.
Sounds good. Thank you.
But first, just compare these two equations, right? Do we have a value now for what equivalent resistance is equal to?
R1 plus R2.
Yeah. Right. The only difference here is the R1 plus R2 and the equivalent resistance, right? These two have to be equal to each other. Right. So when you have two resistors in series, right, to get the equivalent resistance, you just add them together. And that should make sense, right? A resistor kind of, well, it provides resistance, right? And if you have more resistors, that the same current, the same charge has to flow through all the resistors, it's going to be resisted by all of those resistors, right? So it kind of makes sense if you think about it, or it should make sense if you think about it, that to get the equivalent resistance, you just add them together.
Mr. Marcus.
Yep.
I'm trying to get something straight right here. In the equation, right? Delta V. No, where is it? Yeah. Resistance is voltage or delta V over I over the current.
Yeah.
Right. So resistance is supposed to lower the voltage. No, well, it's supposed to lower something.
So when charge flows through a resistor,
right,
it's gonna the potential it's gonna be flowing from a higher potential to a lower potential. Yeah. So
but
the potential V here is gonna be higher than V here, is gonna be higher than V here.
so how come R2 has is gonna make delta V bigger than R1, bigger than the voltage at R1?
Well, okay. Well, delta V and it depends, right? It depends if, because delta V is the change in voltage, right? So, you know, you can have a, let's say, I mean, we can figure out what these resistors, well, we could figure out what, you know, if we gave numbers to these resistors, but let's say we have a 5-volt battery,
Mhm.
right? Then you could have, so that would mean that, you know, if we pick the 0 volts to be down here, right? And then 5 volts would be up here. There's a 5-volt battery. What we might have is, right, so we'd still have 5, it would still be 5 volts here, right? Ideal wires. Then maybe going across the resistor 1 here, we drop down just to say 4 volts. And then that would mean that the potential drop, the delta V of R1 is 1 volt. What would the delta V of R2 be there?
What, -1 again?
It wouldn't be -1 again, right? Because we know that this point in the circuit is 0 volts, right? So that means we can go all the way along the ideal
-4.
wire. Yeah. So this is a delta V of 4 again. Yeah, -4. You're right. This is this is absolute valued, right? That actually yeah, I've just been going with the absolute value, right? This is a positive delta V, and these are technically negative delta V's. So, but we've just been looking at the absolute value. I should do this.
All right.
Maybe that was why there was a little bit of confusion. Did that answer your question?
Yeah, sort of. Yeah.
Sorry. All right. So just to finish up with the resistors in series, basically the same thing. You know, if we added a third resistor, we'd have the same. You know, we'd follow the same process, and we'd get that. You know, we'd have to add plus R3 here to the end. So basically, I'll write down the rule: resistors in series, the equivalent is just R1 plus R2 plus ... So however many more resistors there are, you would add those as well. So that's it for resistors in series. That's kind of the simple one. You just add them together. You want to be able to know that, and also be able to recognize, you know, series means one after another. So are there any other questions or anything else I can clarify about resistors in series and the equivalent resistance?
No, this should be fine. Makes sense.
I agree. Yeah.
Okay,
Parallel
so
ones are going to be a lot harder.
they're not. It's a little harder. Once using it's harder to use the equation. That's true, but it's not that bad. So let's look at
I see.
parallel. Well, all right. So this circuit diagram, now the two resistors are in parallel. I always spell that right. I usually, for some reason, I always spell parallel wrong, but I think that's okay. I always put the wrong number of L's in the wrong number of places. But I think we're good. This circuit diagram shows two resistors in parallel, right? They're in parallel. You can kind of think parallel, right? These two lines with the resistors in them are parallel to each other, is one way to remember. But it's not series, right? These aren't one after another. Charge that's flowing through this circuit is only going to go through one or the other resistor, right? It's going to go through either this path through R1 and back to the battery, or through this path through R2 going back to the battery, right? So the current splits, right? Some charge flows through R1, some charge flows through R2. But then we're going to follow the same process that we just did. We're going to answer the same question. If we want to replace these two resistors with just one resistor that has the same current, at least the same current from the battery, what would that resistor's value be? Right, so we're basically going to replace this circuit now with this equivalent circuit, and we want to have the same current right? The current flowing through the battery. So let's see. What can we say about the potential? So if I've got from here to here, I'm going to say I have delta V1. From here to here, I've got delta V2. What can I say about delta V1 and delta V2 compared to delta V in this situation? And remember that if as you're, the way to think about this is anywhere, any point, you know, along the same ideal wire is going to be at the same potential. So that means the potential here and all along this wire.
Should they equal each other now?
Yeah.
Okay.
They are equal, right? Because this point here is the same potential as this point here, is the same potential as this point here. And this point here is the same potential as this point here, is the same potential as this point here, right? So this potential, so going from here to here is going from the same potential as going from here to here. Do we see that? That the beginnings of each resistor is at the same potential, the ends of each resistor is at the same potential. So that means that, and again, this is absolute value. I'm not going to draw the absolute value signs just to save space. Whoops, not plus, equal. That should be equal, not equal. Let me try that again. Okay. So in this case, if we measure the potential across resistor 1 and the potential across resistor 2, they have to be the same. Questions about why that is? If you're not seeing that, let me know and I'll try to explain it further.
Yeah, I'm trying. Yeah. Shouldn't the end of the whole loop, the potential difference should be 0?
The potential difference is going to be 0, right? We're thinking about absolute value again, right? If this is a 5-volt battery, right, this will be at 5 volts. This is 0 down here.
Mm-hmm.
So that means that this is also at 5 volts here at the beginning of R1. And this is also at 5 volts here at the beginning of R2.
Right.
Right. And since this is at 0, that means this is also at 0 over here. This is also at 0 over here.
Oh.
So going from here to here, that's 5 volts drop, right? -5, really. And going from here to here is also -5.
But okay then, so say we have different, our resistors are different, like they have different resistances or whatever they're called.
Yep. Yeah,
So does that mean that the current changes after that then?
Yeah, exactly. The current has to be different. And you can tell that right away just from looking at R equals V over I, right? R equals delta V over I. If the delta V's are the same and the resistances are different, the I's are going to be different as well, right? And the reason that the currents can be different here, right, is because there's a branch, right? You've got current, this current here flows through here, but then it splits up, right? Some of the charge goes here into this branch. Some of the charge goes through here, through R1 into this branch. So thinking about that, and remember, you can think about it as water in a pipe, right? So the pipe's got a junction, right? Some of the water that's flowing through here goes this way. Some of it goes that way, right? We'll call this one I1, the current that's going through this branch, and we'll call I2 the current that's going through that branch. Is there a way we can relate I1 and I2 to the current that's going through the battery here?
Or we're going to say one plus the other is going to equal the beginning.
Yeah, we can say that the current through the battery is just equal to I1 plus I2. Right, it's kind of the inverse of what we had with the series, right? With the series, we had the currents were equal through both of the resistors, but the potentials were different. Then when we have them in parallel, now the potentials across the resistors are equal to each other, but the currents are going to be different, right? And that's just because still charge is conserved, right? So however much charge per time is going through this branch, plus however much charge per time is going through this branch, has to be the combination of them, right? Because all the charge ends up coming through this branch. Anything need to be clarified for this? This is kind of our starting point for resistors in parallel. And when we get to Kirchhoff's rules, the loop and the junction rules, we're gonna see more similar things like this. That the charge, well, we'll see that at any junction here, right, where a circuit breaks off into two or more parts, the current coming in has to equal the current going out, which is basically the same thing that we're writing here. So let's see what we can do with that, right? I know that. I know if I rearrange this equation in terms of current, right, I get current equals delta V over R. So let me replace current 1 and current 2 with delta V1 over R1 plus delta V2 over R2. Okay, so I have I equals delta V1 over R1 plus delta V2 over R2. So let me put that here. And remember, delta V1 and delta V2 are both just equal to delta V, right? So I can drop the 1 and the 2, and I can say that the current is equal to delta V over R1 plus delta V over R2. And if I look over at my equivalent circuit, right, that's simpler to figure out, right? The current here is just delta V over my equivalent resistance. Right? That's the only resistor there. So let me set these two equal to each other now, right? The idea is we want this resistor to be such that the current going through the battery is the same in both cases. So that's why we have I here, and these two have to be the same. So we can set these equal to each other, and we get delta V over the equivalent resistance equals delta V over R1 plus delta V over R2. Now I've got a delta V in the numerator in each term here. So if I take this whole equation and divide it by delta V, I just get 1 over equivalent resistance equals 1 over R1 plus 1 over R2. And that's the rule for resistors in parallel. So let me, and it actually is the same. If we have more than 2 resistors in parallel, right, we could keep adding branches, right, to this circuit and have more resistors in parallel. What we get for resistors in parallel, I spelled it right again. So 1 over the equivalent resistance, and sometimes you'll see it, well, we'll write it this way. 1 over equivalent resistance equals 1 over R1, 1 over R2, plus ... if there's a bunch more resistors. Right? So what we can see actually is that the more resistors you have in parallel, the smaller the equivalent resistance is going to be, right? That's the opposite of resistors in series. When we put resistors in series together one after another, right, the equivalent resistance was just R1 plus R2 plus R3. So more resistors in series means more resistance. But it's different with parallel. In parallel, more resistors in parallel means less resistance. And that's kind of just because the charge, the current, has more options, right? More places it can go through, right? If you have a really big resistor here, but then you put a really small resistor here, well, then the current's going to flow much more through the small resistor, right? It's easier for the current to flow through a small resistor. So more resistors in parallel actually means less total resistance, right? It's because it's easier for current to flow when there's more branches, more paths.
Yeah, because Mister, it's 1/R. So the greater the resistance you have
Mhm.
for one of them, and the less resistance you have for the other one, is kind of just gonna
Exactly.
decrease the number.
So that's resistors in series and parallel. Any questions about what we looked at today? Right, we'll see that we'll look at capacitors in series and parallel in a little while, and we'll see that the rules are exactly the opposite. Capacitors in series look like this, and capacitors in parallel, you just add them together. But we'll see why when we get there. Okay, so we'll stop the lecture there for today.